Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, now that you understand how basic multithreading works, we're going to start looking at the actual A3C code. The first file we're going to look at is main.py. At the top we have most of our usual imports, such as NumPy, Matplotlib, and TensorFlow. For threading, we'll also want to import the threading module and the multiprocessing module. From our nets.py file, we're going to import a function called createNetworks, and from our worker.py file, we're going to import the class worker. Next, we're going to define some constants. First, we have our environment. So while A3C works on multiple Atari environments as well as some non-Atari environments, we're going to stick with breakout, since that's what we've tuned the hyperparameters for. We're going to set max global steps to 5 million. This is just like our previous basic threading example, where we had a total number of combined steps for each worker to do. Finally, we have a variable steps per update. This is going to be the number of steps each worker performs before calculating the gradient and sending it back to the global network. Next, we have an environment function, which just makes it a little more convenient to create our environment. We'll be using this multiple times, which is why this is useful. Next, we're going to manually set the variable numActions. Remember that breakout is kind of annoying in this way, where the environment contains actions that actually don't correspond to actual actions in the game. So while the real number of actions is 4, it's going to return 6. The Pong environment does this also, so for breakout in Pong, we're going to set the number of actions manually. Next, we have the smooth function. As you know, the total return at each episode is going to vary by a lot, so the final plot of each return per episode is going to be very noisy. In order to smooth out some of this noise, so that we can see the overall trend more clearly, we're going to take the moving average of the returns with a default window size of 100. Next, we're going to get numWorkers, which is the number of workers we're going to create. To get this number, we'll call multiprocessing.cpuCount. The first thing we're going to do inside the with block is create a TensorFlow variable called global step. Now, if you look closely, one thing you might realize is that it looks like we're not going to use this variable anywhere. Internally, however, TensorFlow requires this for some of the computations we're going to do. So if you try to remove this, your code should actually break. Perhaps this is just bad design on TensorFlow's part. Next, we're going to create our global value and policy networks. To do this, we're going to use the scope called global. As you can see, both of these networks are returned in one function call, createNetworks. You'll see why that's convenient later in the code. Next, I'm going to create an iterator called the global counter. This is just like the one we had in our basic threading example. It's going to make sure that we only go up to a predefined number of combined steps. Next, we create a returns list variable, which is going to store the returns achieved by each individual worker. This is what's going to keep track of the performance of our algorithm. Remember that when you pass a list into a function, it gets passed by reference, so each worker is going to be updating this same list. So this returns list is a global variable, which all the workers have access to. And since we're only appending numbers to the list should be thread safe. Next, we're going to create our workers. This is again essentially the same as we had in our basic threading example, just that these new workers have more arguments. So we're going to pass in a worker name, which is just the string worker concatenated with a number, the environment, the global policy network, the global value network, the global counter, the returns list, the discount factor gamma, and the maximum number of global steps. Hence, the worker knows when to quit by checking the global counter and comparing it to the maximum number of global steps. Next, we're going to start a TensorFlow session and launch our workers. As usual, we have to start by running the global variables initializer. Then we have something new, which is TensorFlow's coordinator object. The coordinator object helps us to coordinate the termination of the threads. You'll see that this is like the join function we used in the previous threading example. Next, we're going to loop through each worker and create a set of threads that calls each worker's run function. Once we've created the thread, we start the thread and add it to our list of threads. Outside the loop, we call the coordinator's join function on the worker threads. Notice how this lets us set a grace period. Basically, each thread is going to try to stop at some point, and at that point, they have 5 minutes to actually terminate. If they don't terminate by the end of the grace period, the coordinator will raise an error. Finally, the last thing we do in this script is plot the returns we collected. In addition, we're going to plot these smooth returns, so you can see more clearly the improvement over time. In the next few lectures, we'll look at the other files for this example, nets.py and worker.py.